Okay, dokie. So I think with that, we're ready to get started. Welcome everybody, and good morning, good afternoon, and good evening, depending on where you are in the world. We're lucky to have a very global audience here with us today to talk about a new multi-phase flow material balance method that was developed by different engineers at Cimarex, which is now Coterra Energy, and we're lucky to have them with us here today. My name is Matthias Carlson, and before we start, we're going to go through a few logistical items related to what we're going to talk about today. First and foremost, and most importantly, we have more than 300 registered participants today, so obviously we can't be unmuted, at least all of us. So we're using the system called WebEx events, which makes everybody muted by default. However, that doesn't mean that you can't be interactive throughout the webinar. You can ask questions in the Q&A chat box that you find down to the right here. And just want to emphasize that there's a difference between the Q&A option and also the chat option right there. So use the Q&A when you have answers or questions, and then we'll try to answer them in the Q&A session after the webinar. I'll do a short introduction, and then Leslie and Narayan will do 45 to 60 minutes of presentations followed with Q&A. So if you have questions, those questions will be covered after their presentation. Also worth noting is that we're recording this webinars, and we'll send that out to all the participants after the webinar today. That will also be available on Whitson Academy, which is our online learning platform. That's a subscription item where companies can get access to live virtual courses that we hold every single year, live topical webinars, and also a lot of pre-made courses that you find on academy.whitson.com, including how-to videos and tutorials of how to use different softwares. Example of courses is typical things within the realm of what our expertise at Whitson is, and we are trying there to cater for a wide range of levels, not only experts, but everything from beginner, intermediate, and experts. The public courses that we're holding at Whitson is already online for next year, so you can go into whitson.com/training and get an overview of that. There you also get an overview of the upcoming webinars also for next year, so you can go in there and register as well already. And new courses and new webinars will be frequently updated on the website as we get more courses and more webinars available. Then over to what we're going to discuss today, which is something that at least internally at Whitson we're extremely excited about, which is a new multi-phase flow material balance method that does not require relative permeabilities as an input. Just to set the stage a little bit, there's essentially two main or major problems with existing multi-phase flow material balance methods. And in short, the first thing is that it requires relative permeabilities as an input, which is one of the most uncertain call it inputs to any type of reservoir simulation, numerical simulation, etc., or these exercises. And also the resulting diagnostic plot in many cases it looks like, or in most cases, it looks like a gunshot. So it's extremely hard to interpret. And with these two fundamental problems at hand, Leslie, Barry Ruddick, and also colleagues at Cimarex, such as Narayan, developed and created this method that we're going to discuss today that does not require relative permeabilities, has a diagnostic plot that's easy to interpret, that has been tested on hundreds of field cases, and also been benchmarked against simulated cases, and I've done that myself as well, and it's almost a spooky exercise because you're running, you can run full physics numerical models where you have the answer, you know what the rel perms is that you're putting into the model, etc., and then you're using this workflow and you get the exact results out in 6 seconds without anything else than rates and pressures and PVT. And also worth mentioning that this method was developed at Cimarex, which is now Coterra in the recent years. The key diagnostic plot that we'll see a lot throughout the course looks something like this, where the slope of this line right here is telling us something about the pore volume. Okay, so we'll go back to that in a second. We're also proud of mentioning that the method is available in Whitson Plus now with the next release that's coming out tomorrow or on Friday. So for those of you who don't know Whitson Plus, that's just our web-based software suite that includes flow material balance, RTA, bottom pressure calculations, decline curve analysis, numerical modeling, and PVT. So it's available already tomorrow. It includes some intuitive drag and drop functionality. And it has some very nice features, including the ability to link it to a recovery factor analysis feature, such that you can do this type of work very, very efficiently. Just to show that real quick of how it looks like in the interface, the flowing material balance features are down here to the left, and this is the multi-phase flowing material balance feature that we'll talk about today, where you see that when I change the slope right here, the pore will be updated. That's also linked to a recovery factor analysis module. And that module I'll not talk too much about today, but that's essentially a way for you to forecast also your relative rates and pressures, and link that with your multi-phase flow material balance exercise and get some recovery factors for all the different fluids inputs. So on that note, we should be good to introduce the speakers. Today Barry Rudek, he was supposed to be here, but he could unfortunately not make it, but he's been very key in the group of people at Cimarex that's been developing this methodology. We have Leslie Thompson with us here today, which is a senior reservoir engineer with Coterra and Cimarex. And before that, he was many years at Tulsa University. And he's also going to co-present together with Narayan, which is the chief reservoir engineer at Coterra, which has a background from both University of Texas, Austin, and also Lynn Energy, and of course, much more. So on that note, Leslie, I'll just make you a presenter right here, and I'll go ahead and mute myself, and good luck.
You guys with me? Can you see it?
Yep, there we go. Perfect.
Okay, so today I'm going to talk about this method that Barry Rudek and I developed between 2016 and 2017 to try to get estimates of original fluids in place. So the way this is going to work is I'm going to present the first half of this talk on the theory. And then Narayan here is going to come in the second half and present some field examples. Narayan was not here while we were developing it, but he is by far one of the largest users or biggest users in Cimarex for this technology, and he has a lot of experience with the field with him. Okay, so very quick overview. Basically, Matthias took all my thunder, but it's fine. So basically, this is just a technique, plotting technique for analyzing multi-phase flow data and getting estimates of drain reservoir volume and fluid in place. And the only requirements are standard production rates of oil, gas, and water, bottom hole pressures, modified black oil properties, standard densities of oil, gas, and water, and then initial reservoir conditions, saturations, and pressures. And as Matthias showed, this technique results in a straight line. The slope of that straight line is the inverse of the drain reservoir volume. Okay, so why are we doing this? Well, it's pretty obvious, but anyway. So one of the biggest jobs of a reservoir engineer is to create rate forecasts, but those forecasts have to be constrained by what is actually contained in the tank. And we have several methods of doing that, petrophysical models. If we have single phase flow, then we have nice static and fluid material balance methods. Multiphase flow, historically, people used tank models and material balance methods as well. But it's clear that, that nowadays, especially with our unconventional reservoirs where you have really low permeabilities, etc., we need semi-analytical fluid material balance techniques for constraining these the reserves in place. Now, there's obviously at least one other method available that uses pseudo pressures to try to make the multi-phase flow equations look like single phase flow equations, and then use single phase techniques on it. You know, that's fine. It's a tool. I think you should use it if you have it. Today we're just going to present you with another tool.
Leslie, just one question. Can you speak a little bit closer to the microphone? A little bit louder. Thank you.
Is this any better? So the theoretical basis. Am I coming through clearly?
Yeah, that's better. Thanks.
Okay, sorry. Okay, so it's based on a hypothesis, and hypothesis is that during pseudo-steady state for boundary dominated flow, all points in the reservoir will decompress at the same rate. So where does that come from? Well, 40 years ago, I was a graduate student in the University of Tulsa, and my first course in pressure transient analysis, Dr. Raghavan, he had derived the pseudo-steady state flow equation for for a slightly compressible fluid, and he showed that the P by dt was inversely proportional to the pore volume. And he asked the class, well, so what's the physical significance of the P by dt being constant? And of course, we all young engineers had no idea what the hell he was after, and so nobody could answer it. And he eventually said, well, there's absolutely no significance to the P by dt being constant. What is physically significant is that during pseudo-steady state flow, the rho by dt becomes constant. And because the fluid is only slightly compressible, you can show that that translates to the P by dt becoming constant. And that idea kind of stuck in my head. So 35 years later, when I was looking at this for all the reservoirs, I'm trying to figure out there must be some better way of doing this thing. I wondered whether that hypothesis would work. So again, this idea is not mine. People have I've seen it in different authors over the years. People have mentioned it, but as far as I know, nobody ever really fully developed and explored it. So I just want to emphasize this is not derivable as far as I know from basic flow equations. It's a hypothesis. And since it's a hypothesis, you should take it with a grain of salt, and we use a scientific method. We not test the hell out of this hypothesis, and if it fails, we just throw it in the garbage heap. But if it doesn't, then perhaps we have something that we can use to actually try to get some useful information from our reservoir. So some basic definitions. So we define in situ mixture density as beta. Don't ask me why beta. I just chose beta off the top of my head, and it's given by this thing on the right-hand side here. For those of you who work with the multi-phase flow, PDEs for oil, gas, and water, you recognize the right-hand side as a combination of the accumulation terms on the oil, gas, and water components. Okay, I've just put the densities in, and so the units on this are actually density. It represents the mass, the total mass of oil, gas, and water components in a unit volume of rock. So it's indeed a density. Density change is just beta I minus B minus beta. The mass rate is just the total mass rate of oil, gas, and water flowing out of the reservoir at any particular time. Mass material balance time is just defined as the cumulative mass divided by the instantaneous mass rate. And our hypothesis, if you put it mathematically, is just that the derivative with respect to material balance time of the mass rate normalized density change is a constant. And that constant is exactly 1 over the pore volume. This, by the way, is exactly true. You can prove it exactly for a tank. And a tank, of course, you just have one pressure and one saturation at any particular time. And you can show that this is exact. The question is, does this work for a real reservoir, which is obviously not a tank. And so that's what we're going to try and test. So when I showed this to Barry, he said, well, no way, this is not, it's pie in the sky, it can't be right. So let's test it. So first thing we did was integrate our assumption at the wellbore, and we got our flowing material balance equation. And that simply says that if I plot the change in density at the wellbore, normalized by the mass rate versus mass material balance time, I should get a straight line again with pore volume, with slope 1 over pore volume. So to test the hypothesis, what we did is we created a suite of different simulation cases, reservoir simulation cases. We chose 4 different reservoir geometries as kind of representing what we thought we would have in our fields or something similar. We used 3 different fluid types, and those fluid types represented again types of fluids that we saw in our reservoirs. So they were lean gas condensate, rich gas condensate, volatile oil. Later on, we tested with black oils as well. We tested with 2 different relative permeability curve sets and initial conditions above and below the bubble point. And we used pressure drawdowns, again, similar to what we would observe in the field. So nothing was run at constant rate or constant pressure. Everything was run with what we thought were more realistic sort of pressure drawdowns. So, and the question we're asking is this hypothesis reasonable? And so I'm just going to show you a couple of examples from one geometry that we ran. I just want, and these are just production data from the simulation. And I just want to again point out that the black line on these curves is the bottom hole pressure schedules that we use. And so there's nothing here about constant pressure nor constant rate. So this is for volatile oil, lean gas condensate, rich gas condensate. Again, when we plotted all these things using our technique, they all approached straight lines with the slope equal to 1 over pore volume. Now, they take, the time at which they get to that straight line depends on the geometry. It depends on the fluid that is present, but eventually they all get there. This plot here on the right-hand side is just spanning 1 year of data. But if you continue, for example, so these lines are all, as I said, approaching the correct volume. And the top one is obviously approaching it a lot less quickly than the lowest one, which is the volatile, I guess, the lean gas condensate in this case. Okay, so that's fine. That worked in the wellbore, but our hypothesis was that that the reservoir decompresses at the same rate everywhere. So what we did was we ran a more complex geometry example. We put in different fractal lengths. We put in a wellbore that was not perpendicular to the fracture, so it was this diagonal line that you see going across the different fractures. And we monitored 6 different points in the reservoir all over the place, and wanted to see again, does this work at different points as well? And again, when we calculated our rate normalized density change versus material balance time at those points, again, they all eventually got to the correct straight line. So, we did, I think, a total of 72 tests with really fine simulations using a research simulator from University of Tulsa. Dr. Rami Yunus gave it to us. And in all the cases we tested, the method held up, regardless of fluid type, relative permeability curves, drawdown schedule, you name it, it held up. Okay. Since that time, we tested again. When Narayan came, of course, he was also skeptical. He tested again using different simulators, different initial conditions, different fluids, relative permeability curves, using CMG sensor, OPM flow. All of them gave the same results. Okay, so that's pretty encouraging. So let's kind of look under the hood now, because it's not too obvious. How the hell do you calculate these densities anyway? So So as I said, but our definition of density is this beta term that we have here. And this beta term contains PVT properties, which are, you give me the pressure, I can give you the PVT property. These are pure depletion processes we're looking at. So you don't have anything like changing bubble points or anything like that. You give me the pressures, I give you a unique PVT. The only problem that I have here is these saturations. What do I do with those? Okay, so when I first started thinking about this, I thought, well, when you first open a reservoir, the very first thing that happens, in the first couple of seconds, is that the region right next to the fractures is going to be depleted. That's what's producing to your wellbore. So all the fluid is actually coming from a very, very small volume, very close to the fracture, maybe a ½ inch wide, I don't know, ½ inch, 1 inch, whatever. And in that little region, I'm going to assume in those first couple of seconds that the average pressure in that little region is very, very close to the wellbore pressure. And if I do that, I can do a material balance just on that region. And I can say that the total amount of oil, gas, and water that I produce during that first couple of seconds is the volume of that little region, which, by the way, I have no idea what it is, times the change in density. Well, I don't have density terms. It's change in accumulation, basically, for each of those phases, or each of those components, sorry. So you can see I have a little bit of a problem here to start with. I don't know what VP small is, but we'll put that aside for a second. Now, after the first couple of seconds, your first set of production, you have a new problem, because either you can look at this thing of one of two ways. You can say, well, that small tank region is now going to start growing with time. And if you do that, that's fine. Except now you can't say that the average pressure in that little region is the wellbore pressure anymore. And here's where Barry really sort of jogged my whole thinking about this. He said, hey, don't let that small tank region grow. Instead, keep it right next to the well, keep the average pressure at the wellbore pressure, and then do a material balance on it still. So now, after that first couple of seconds, what I have is fluid flowing from the reservoir across the small tank region. It's joining with the fluid that comes from that small tank region, and it's being produced. And so I can still do a material balance on that small tank region, provided I call these cumulative productions net cumulative production. So it's a net oil, gas, and water that's coming from that small tank region. Now that's kind of a problem, because again, what I'm actually measuring is what's coming out of the entire reservoir. I'm not just measuring what's coming out of the small tank. So now I have two problems with these sets of equations here. The first problem is I don't know what BP small is, and the second problem is I actually do not know what these net cumulative productions are either. So let's continue, and let's take the first problem out. So we can get rid of not knowing the volume by simply taking ratios of any two of these equations. If you do that, what you get is net cumulative flowing ratios. So the net oil gas ratio flowing out of that small region is given by this ratio here, and the net water gas ratio similarly is given by this thing. Now, as I said, we still have a problem. We don't know what the net oil gas ratio and net water gas ratios are yet. I'm going to put that aside for a second, but let's assume that we knew it. If we did, we have two equations here, and then there are three saturations that I don't know, the oil, gas, and water saturation, but I have a saturation constraint. So basically it's two equations and two unknowns, two saturations, any two that I want. And therefore, if I were to know those net cumulative flowing ratios, I could explicitly write down what the saturation is in terms of those ratios. Okay, so we still have that one problem to deal with. What are these flowing ratios? So again, if you go back to the little model that we have of what's happening in the reservoir, if you notice everything from this reservoir, whether it's from the small tank region, which is a subset of the entire reservoir, or the entire reservoir, is flowing at exactly the same instantaneous fluid ratio. Okay. So, I mean, they're both experiencing, whether you're talking about a small tank or you're talking about a big tank, doesn't really matter. both of them are experiencing exactly the same relative permeabilities, whatever curves there are that apply to the system, and they're both producing at exactly the same instantaneous GOR. Now, you can do a little bit of math with that, and you can then argue that the cumulative fluid ratios from both regions would be close. They would not be identical, but they would be close. And our hope was, well, if they're close enough that we can make a good enough relationship between pressure and saturation to compute our in situ densities at the wellbore. So that's exactly what we did. So the workflow summary is, to boil everything down, everything depends only on production and PVT data. And the method is extremely simple. It is not iterative and can be programmed in Excel. In fact, this is kind of my last task at Quotera Cimarex before I actually am severed and go into whatever, semi-retirement or whatever. My last task was to transfer this technology to Whitson so that it could be continued to be used by Quotera engineers. And everything that you see here was transferred to them in Excel sheets. I don't recommend that you use Excel to do it. It's very cumbersome and slow, but it's simply enough to be done that way. So that basically ends my part of the talk. So I'm gonna turn this over to Narayan, and he will talk about the field examples. Thanks.
Very good. So I made Narayan a presenter. There we go.
Can you see my screen and hear me?
Yep, excellent.
All right. So we've gone through the theory so far with Dr. Thompson, and I should qualify that this method had already been invented by the time I showed up at Cimarex Energy, and my first few years was field testing this method on actual field data, and that's why I'm doing this portion of the presentation, and also running every other available workflow concurrently on the same well, try to understand what the limitations, the strengths and weaknesses of this method are, and also throw in all sorts of practical complexities that we would understand that are happening in a reservoir and viewing it in this context of a flowing material balance. So the way we, again, the requirements to do this are production data and calculated flowing bottom hole pressure from surface rates. In most of our wells, we have gauge data, so we're fortunate that our flowing bottom hole pressures are measured. This was combined with PVT properties initially using correlation, standard industry correlations for black oil PVT properties, and later switched to an equation state model for predicting modified black oil PVT properties. So that's kind of the evolution. Everything was done in a web app, and now we have this flowing through Whitson Plus. Next slide. The four field examples that I'm going to walk through are with a purpose of kind of walking you through our evolution of how we interpret the multi-phase flowing material balance. The first example is going to be an Anadarko Basin Merrimack oil well. There's sufficient production history on this particular well. And then I'm going to talk about a couple of Delaware Basin examples. So the progression is it's going to go from volatile oil to a gas condensate as we work our way through these four examples. So I'm going to take a minute to explain these charts here. This is going to be a very similar format for production charts going forward in the presentation. So I'm going to take a quick moment to introduce the axis because they're not quite as visible as they should be. Rates are on the top left chart, and the axis, it's a log scale. It's on this axis scale right here. We have a couple of things plotted here on the bottom left chart, which is ratios and flow and bottom hole pressure. So I've annotated this well example starts off at an initial GOR of 600 SCF for stock tank barrel. It's a volatile oil reservoir. And this ratio right here is GOR, and this is the flow and bottom hole pressure. So you can quickly examine the scale right here. Most of the data is going to fall between 1,000 and 10,000 units. So it's going to start off at 1600, and this particular reservoir is overpressured. It's going to be something close to 7,000 to 8,000 psi initial reservoir pressure. And I've added a couple of reference charts here for cum gas versus rate versus Q for the oil phase and the gas phase, just to give you a visual estimate of the quality of this well. It's a fully bounded well. What we call that is we think conditions of boundary dominated flow / pseudo steady state flow should be pretty valid for a fully bounded well. So I'm going to start with what we think is an ideal example for this application here. Next slide. So first chart on the right are the individual phase saturations. This is the material balance equation solved for individual phase saturations that Leslie talked about just briefly. It's using the instantaneous ratios at the wellbore, water, oil, and gas ratios, to back into what the tank average saturations are with, as clarified earlier, you need an input. So in this case, it's an undersaturated oil reservoir. We need an input, and the input was 20% water saturation. And the resulting oil saturation being close to 80%. So as we solve the tank material balance at flow and bottom hole pressures, what you get is a material balance solution to oil saturation, which should look very familiar to anyone who's worked with PVT data. And as we approach the saturation pressure, the gas saturation in the reservoir increasing and a slight decompression of water saturation. So first step, as we said, use production data and the instantaneous ratios to back into oil, the in situ phase saturations or tank average phase saturations, and then them converted into, using the mixture density term that Leslie introduced, into mixture density, mass flux, and a mass material balance time. So this is an example of field data in this multi-phase flowing material balance plot view. I'm going to walk through what we think are 3 different regimes that we're seeing in the production data in the next few slides. Again, y-axis should be familiar by now. It is density over mass rate and mass material balance time on the x-axis. And as I showed you in the previous slide, we have a little more than 2 years of production data on this particular well. So how do we interpret this? Where do you draw a slope? And that's what you're wondering. This is where our 3 years of experience hopefully gives you an idea of how we interpret these wells. And that's the purpose of the next few slides going in. So why do we see a concave up and a concave down behavior? What's this here? So let's kind of walk through what we think are 3 regimes in the production data in this particular well. So what I'm going to do here is, this is the top left chart is the flowing material balance plot. I'm going to highlight what we think is the first regime, and I'm going to call this a low system compressibility and high diffusivity regime. And the reason why is, if you look at the flowing ratios, the GOR in this case, and the flowing bottom hole pressure, it is the portion of the data in which the reservoir is undersaturated. So it's interesting that you have this shallow slope that's associated with low system compressibility and high diffusivity. In other words, if we calculate the mixture density term that Leslie introduced, and then look at what the oil density phase, the component density of the oil and the component density of the gas is plotted versus pressure. The pressures in the reservoir are about saturation pressure, so the compressibility is lower, and you're essentially seeing a high diffusivity term. And what we were surprised by is how quickly this transient kind of propagated through the reservoir. And we get what we think is an estimate of the pore volume in such a short duration of time. That was a surprise to us. But I'm going to walk through these flow regimes here. So the first one is a low system compressibility, high diffusivity, above saturation pressure flow regime. And you can anticipate what's going to happen next as we drop our pressures. Now you start seeing this portion of flow when you have a drastic change that's associated with gas breakout. So the system compressibility increases. Mixture density, as you can see here, gets nonlinear. And you essentially see a concave up behavior that's associated with a decreasing diffusivity, which is associated with gas breakout. And you can see that manifested in production data with an increasing ratio. So this is high gas breakout, increase in GOR. You associate that with basically the system is in going through a transient that's associated with gas breakout. The next regime is regime 3 as a pressure stabilized. Now your pressures are below 1000 psi, your ratios are relatively stable, and you're in depletion mode, and your compressibility, the rate of change of the compressibility of the system decreases. And now this flowing material balance method is able to get its densities in order, as we like to call it. And now you see the concave down behavior that's associated with long-term production data. So this is a way, when we showed you the first plot, the 3 flow regimes that we think of for this particular volatile oil well. So the next question is, how do you interpret the pore volume? In this particular well, since we're fortunate to have long production data, my interpretation for the pore volume is going to be associated with this slope that I've drawn here. The rationale for drawing the slope right here and a fascinating empirical observation is this slope is not that different than what we realized during undersaturated flow. It's a remarkable observation that we've seen in undersaturated volatile oil reservoirs. And the implication of that is, we do this as we work with field examples, is we get a signal for what we think is the long-term contact or pore volume that you potentially need 2 years of production data for in the first few months. This line right here that's displayed is basically the same slope as a pore volume pick, just reference at a zero intercept, so you can visualize what the slope looks like with the early term data. Once I pick a pore volume, once I pick a slope, the pore volume is inversely proportional to the slope, and you back, as you're probably not very familiar with, in this case, it's 3.1 million reservoir barrels. And once you have a pore volume estimate, you can back calculate what the average reservoir pressure of the tank is, which is displayed in this golden curve. Also displayed is a pressure versus time plot, is the flowing bottom hole pressure of this particular well, which introduces a constraint that you have on the system. If your pore volume estimate's way too conservative, you'll notice the delta between average reservoir pressure and bottom hole pressure decrease. So there's some constraints on how low and how high. Perhaps not on the high side that you have for your interpretation of pore volume. And again, to bring it to units that are more relatable, I'm going to convert the pore volume using volumetric equations into what the original oil in place associated with this drained volume is. So if you work out the equation, so for this undersaturated oil, it's basically pore volume times the saturation of oil divided by formation volume factor of oil. You get 1.4 million barrels of oil contacted. For gas, it's just going to be your oil in place times RSI, or your initial solution gas oil ratio, which works out to 2.3 BCF. And we have treated the system as with some mobile oil in the reservoir, arguable, but that's just how we've interpreted this well. It's 0.6 million barrels of water in place. So this is a typical interpretation. Hopefully I've kind of walked through this systematically. You understand what this means. And once you have an in-place interpretation of oil in place and gas in place, you can obviously pair it with an expansion drive recovery factor to get an ultimate recovery estimate, which is not in the scope of this presentation. The next example I'm going to talk about is a Delaware Basin Wolfcamp oil well. It's a very different system. As you would expect with the Delaware Basin, you're going to be producing a lot of water. The water cut's going to be north of 80%. I'm sorry, this is a mistake. This shouldn't be here. And the initial GOR of this well is 3,300. And if you can look at the initial reservoir pressure here, it's going to be close to 4,000. So nowhere close to be in a highly undersaturated oil. You can see the oil and gas rates. You can see the productivity of the oil phase been relatively high. And here is an example. This is the example that Matthias showed in his web interface here. So you should be familiar with the phase saturation plots of the tank average saturations. Right here, the input in this case was 70% water saturation that's associated with a high water cut. And once you do the tank material balance, you end up with basically a saturation of oil that's decreasing and then associated increase in gas saturation that's not known. And what you'll notice is this basically starts off at saturation pressure. So you do not have an undersaturated, reasonable undersaturated flow in this particular well. Similar to the previous well examples, you see the 3 different flow regimes. And I should have qualified, this is an unbounded well. So that's what's different with the example that's previously shown. This is an unbounded example. And the rationale for picking the pore volume here is it's what we saw during undersaturated flow here. And if you visually examine this data, you'd say, well, that doesn't fit the data. And again, the rationale is based on the shallow portion, the undersaturated flow period, and the other constraint that at all given conditions here, back estimated flow and average reservoir pressure should be above your flow and bottom hole pressure at all given times. So a buildup, an inadvertent buildup, in this case with downhole gauge data, is a good calibration point for what your pore volume could be. Similar to what we did with the Anadarko example, we estimate a pore volume that is substantially larger because of the higher water cut and the higher total mass flux out of this well. Oil in place at 3.3 million barrels of oil, 11 BCF, and 21.4 million barrels of water. Again, another takeaway and a relative comparison to the previous example is this is unbounded. So what you'd notice is the third flow regime is not as well established. Since we haven't adequately drawn or gone into depletion mode for this well being an unbounded well, and we were not able to see in the long term, since the flow regime 3 wasn't substantially established, our pore volume is a minimum at that point. Hopefully that clarifies the flowing material balance can be conservative in instances such as unbounded wells. The next example I'm going to be talking about is a Wolfcamp Gas well, Delaware Basin. It's a fully bounded well, and that annotation that I had for water gas ratio should have gone on this chart. It's roughly 550 stock tank barrels per million. The initial GOR for this gas well is close to 4,400 scf per stock tank barrel. You have oil rate versus Q and gas rate versus Q. And what's interesting about this example is, if you remember the examples that Leslie showed you, you see the concave down behavior in the synthetic examples. That's what you see when you hop over into the gas window, in this case, a near critical gas, is you no longer see that low system compressibility, flow regime 1, as we identified in some of the oil reservoirs. So hopefully that gives you context as you hop over into the gas window, you have to be patient with the data. You need long duration of time to get to what you think is a reasonable mean subjective term estimate of contacted pore volumes and in-drain fluids. So for gas reservoirs, it is, as we always do, you have to apply multiple workflows on the same production data. I just want to clarify that you need to be patient with gas wells. And again, your one tool that you have to help calibrate yourself is the average reservoir pressure at all conditions. At all times should be higher than your flow and bottom hole pressure. The next example is an unbounded Woodford gas well. It's going to be the leanest of the 4 examples. Its initial GOR is 7,600. You have the rates. There was a scheme for the 2 phases. It's an unbounded parent well. So this would be one that's going to need even more time to see its contacted pore volume. This is not gauge data in this particular example. Similar to what we've shown before, here's the saturations, tank average saturations. And there's some hysteresis here that is fascinating. Again, it's not the scope of this presentation, but again, the concave down behavior that we're seeing and associated with these wells is, if you give enough production time, there's a concave down behavior. And you would expect, as this well continues to drain and eventually sees flow regime 3, if it does, it's going to continue concaving down. So hopefully that clarifies. For undersaturated oil reservoirs, you might get a signal. For gas reservoirs, what you're hoping for, these estimates of pore volume are going to be extremely conservative if you only have the first few months of data, so you have to wait for it to concave down. At all points, these estimates are going to be conservative for gas wells. It's a minimum. Here's a summary table of the 4 field examples we've kind of walked through today. What's interesting is the range of pore volumes that might not be intuitive to you, and the reason for example, this particular well, do we have such a large pore volume that's associated with the high water cuts and hyperactivity. This number is very instructive for us as far as trying to understand what the tanks of our infill wells are. It helps us, that in combination with the recovery factors are 2 metrics that we track on all our infill wells. So here's a summary of our observations for the field examples. We have done drain volume, reservoir volume, and original fluid in place, estimates for wells in a wide range of PVT types. It obviously works. The method's identical for a gas in situ or an oil in situ. All you need is a modified Blackwell PVT table paired with your production data. Our observation and empirical data is bounded wells in oil reservoirs see their drain volume very early in the production life. This has great practical implications of being able to apply this analysis in the first few months. Conditions of boundary dominated flow may require a long production duration in situ gas. I hopefully have covered that with the last 2 examples. And ending with concluding remarks. Cimarex Nocotera, we have applied this method on several thousand wells now. I did the count yesterday since 2018. It is one of our standard workflows that we apply on all our wells because we are almost 90+% of our well data set are the liquid-rich unconventional wells. There will be a follow-up session if there's interest on how do you pair what the tank volume is with the expansion drive recovery factor to estimate what your ultimate recovery is going to be. As Leslie hinted, for someone, as many of you on the call have been working with volumetric rates, this is a shift in thinking to masses and densities, right? We're used to thinking in pressures and volumes. So like many of you on the call, I was about as skeptical as many of you. And over the years, as I've done concurrent workflows, run really complex simulations, taken the outputs, you name it, in terms of complexities thrown at this method, it is spooky, as Matthias said, how well this method works. It is remarkable. It's fascinating. Give it a shot. Well, you're wondering why are we releasing this method? I think our executives made the right decision to release this method. I think it is, from a science standpoint, it's the right decision. And our rationale is once we get this method out there in the hands of people who are smarter than us, there will be some innovation. There'll be a better understanding of why certain assumptions pan out. And there's a lot more innovation and research to be done on this method. There's a lot we don't understand. So that's our rationale, and that's our last slide. And that's all we got. Matthias?
Excellent. So we have so many questions coming in here on the chat and in the Q&A as a part as well. So I'll try to go through them a little bit systematically. There's a lot of them that overlap, so it looks like a lot of people have very similar questions and concerns. But I would just like to add to the last comment that Narayan had that I probably was equally skeptical to the method the first time I tried it. So, you know, when you're skeptical, you just have to, you know, not speculate, but calculate. So get in front of a simulator, run some synthetic cases where you know the answer and test the method against that. You know, start with simple cases, then move on to more advanced cases. And that's the way you will convince yourself. And once you're convinced, you're then in a good situation to start using this in actual field examples as well. The first thing that I think would be very, very relevant to answer, and a lot of people ask this question, is this methodology published anywhere? And if so, can we get the reference to the paper? And that's actually a very interesting question, and I'll let Narayan and Leslie respond to that.
You're muted, Leslie. Leslie, you're muted.
Okay, sorry. I'll try to keep the answer as diplomatic and nice as possible and not use words like petty and unprofessional. I submitted this paper to SPIE sometime in July this year. After 1 month, I got an answer back, and I got 3 reviewers. The first reviewer said it was a great paper. There was a few little things wrong with it, but should be published. The second reviewer was more interesting. He had lots of feelings that he expressed about it. He felt that it wasn't right. He felt that things were not as it should be, and he said it was unpublishable. And then the third review, I think, was an editor, and he basically said, he gave a one-liner. He said, I agree with review number 2. So the paper was not accepted. So Barry and I wrote a very long and very detailed rebuttal of all the points that the reviewer gave. And we resubmitted it on August 18th. That was what, almost 4 months ago, I guess. We still have not gotten an answer from SPIE. There's been many times I've just thought, I'm just going to pull it and just submit it somewhere else. People have talked me out of that. I've also said, why not just put it as a white paper on Whitson and let people decide for themselves? And actually, I don't even object to that. That's fine with me. But again, my co-author, Barry, who is absent today, he said, let's wait a little bit and see what SPIE does. So we're still waiting. I don't know how much longer we're going to wait. I'm pretty fed up with the whole situation, but so that's it.
Okay, so submitted to journal and waiting. So that's a good conclusion. But over back to the technical stuff. One question that came up a lot, which I think is an interesting question, and probably the first thing that I remember probably myself as well was skeptical about is, let's say you're dealing with a well that's either in kind of an infinite acting linear flow type of system, or if it's still in a transient. Can you still use the methodology, and how potentially would it look like when you transition from an infinite acting type of system into something that becomes more and more boundary dominated or pseudo-steady state like?
So, Ryan showed some plots where things are concave down and they asymptotically approach that last slope. All the transient part is inside of that concave down part. So even if you apply it to a reservoir that is not in boundary dominated flow, what you would expect to get is at least a minimum estimate of the pore volume drained. I don't know if that answers the question.
Yeah, example number 4 was one that was in a transient flow for several months. So if you look at the early term production data, it was steep, and then over a long duration of time, it concave down. So as Leslie said, if you pick the steeper portion, you're going to get a smaller pore volume that is potentially conservative.
Again, a few other questions is related to how this method compares to other methods. When you've been developing the tool or the workflow, what type of other methodologies have you compared and kind of wedded the results against? And also, when you're dealing with these results, do they agree with call it history matched simulation models?
I'll chime in real quick. Is if like synthetic examples, they'll match, right? Because we know exactly what we input. In empirical field data, we rarely have a good understanding, or can we say definitively that these are the Wolfram curves that apply. So it's subjective. However, good agreement, if I would apply my subjective analysis on a simulation model with the same production history, I would get constrained answers, though over time I've now transitioned to now I constrain my simulation models based on this flowing material balance method. Matthias, you ran the numerical RTA in conjunction with this, so if you have a couple of comments, it would be a good point.
Yeah, so I think that's, I guess, where I'm very excited is, numerical RTA, numerical simulation models. No matter what we do, unfortunately, when we are in the multi-phase domain, we need rel perms as an input, and rel perms is one of the things that you don't measure. There's not good measurements on it, or if you had a measurement, even it's like, okay, is this little measurement in this tiny rock representative of this huge fracture surface area or rock that you're draining? So what I'm very excited about and what we've done is both with synthetic cases and real field data run numerical RTA, where we're essentially constraining some of those inputs on the rel perm side, for instance, to the results that you get from this method. And in that sense, the results have been very, very, very agreeable, which is very exciting. Over to the next question here, which is a little bit more on probably the interpretation side of the plot itself. So there's two questions related to that. One to you, Narayan, here, where it seems like for the oil wells, the early time slope is being prioritized over the later time slope in most of the cases you presented. Is this a general conclusion from your experience when applied to an oil well?
Well, it depends on the case. In the first example, they were consistent, the early term and the late term slope. So since it was a bounded well, in the second well, I did not expect, in the second unbounded well, I did not expect regime 3 fully manifested being a parent well. So yes, in that instance, I prioritized the early term slope because that's the only reliable pore volume estimate that I could make. And to subjective analysis, I compared my tank average reservoir pressure versus fluid monomole pressure, and it seemed reasonable. So in the absence of long-term production data and a definitive concave down behavior, yes, I would prioritize the early term models.
It especially helps too if you have a buildup and with gauge data where you cannot have bottom hole pressures being higher than average pressures as long as the well is actually draining without interference from, say, a bash or something like that. So that also helps as well. But as Narayan said, this is also subjective. It's your interpretation as well.
Very good. So a follow-up question to you there on the plot there, Leslie. Is the density mass rate plot somewhat pressure normalized, or does it assume constant pressure?
There's no constant pressure. It is whatever the bottom hole pressure is at that particular time. And we really rarely see bottom hole pressures being constant. Most of our wells are, I don't know, 5 to 8 years old. I mean, well, the oldest wells might be 5 to 8 years old, and those still are not at constant bottom hole pressures. So no, there's no normalization or anything.
Perfect. Another thing that is a very interesting question that a lot of people have asked about is since you get the saturations out, and since rel perm is not a required input, can you potentially extract relative permeability curves from this type of analysis, and have you attempted that, and how did that work go?
In a nutshell, it did not work. The saturations that we get are kind of tank saturations, and if you think of, even from your old material balance stuff with tanks, saturation that you get in a tank is often not anywhere related to saturation that you're seeing in a reservoir. If you think about it for a second, I can have an undersaturated reservoir at average conditions, which is producing below the bubble point, for example, at the wellbore. So you have you would have GORs and everything that are inconsistent with that saturation, the average saturation in that tank. The problem is that our method seems to give something more closely related to the average saturation, whereas relative permeability is actually corresponding to the saturation at the sand phase. And there's kind of a disconnect between them. So yes, I tried this method. It's one of those on the garbage heap.
That's good. Any comments from you, Narayan, there?
No, I concur.
Perfect. Have you tried this method on wells that is experiencing interference?
Yeah. Yes. Narayan has a lot more experience on this than I do, but we have done it on wells that have been bashed, for example. And you notice that Narayan had put up a plot, and we put in on that plot beside the average density change at the wellbore. We also, sorry, besides the rate normalized density change at the wellbore, we also put in the rate, the average density change divided by mass rate at average conditions. In many cases, if you have a well that was bashed, what you would see is that, you know, suddenly you get a pressure increase, a sudden surge in pressure. You might get a sudden surge in rates of water, for example, and that would cause your data, your wellbore data, to actually fall below that average line. So for a little while, what happens is, we think, is that, you know, your fracture system gets opened up, the well actually sees more than it should, so you get even a shallower slope than you would normally see. Then it eventually come back to what it was before. So after the bash, it would seem like the fractures healed again, and it would go back to what the trend was before. I think that the last case that Narayan showed probably was bashed. I don't know if it was or not, Narayan. Is that true?
I removed the data after the bash, but the answer is yes. We look at data after fracture-driven interaction when substantial, you know, reasonable 6 months of data is available to make a judgment on how much of the tank impact did the set of infill wells that we drilled have on the parent. That's something we track, and I think it's useful.
Yeah, very good. So I think I'm just getting so many questions in here, so we need to probably cut it. I'll take one comment and then one last kind of general question. And then if you all have any follow-up questions, I'm sure the presenters are open for taking those after the fact. I think one comment that was very nice from Dylan was a comment about the you know, other types of technologies in the past that hasn't really been published papers in the first place, but as you know, can still be very, very influential methods in different industries. And I guess the Bourdais derivative is an example I was mentioning here, but you also have other types of technologies that has been leveraged in the industry for a long time, and then the theory has actually been proven tens of years later. So that's a good comment from Dylan there, which might be the case for, or at least relevant in this setting as well. The last just general question to both Narayan and Leslie is, you know, Leslie, you mentioned that you can do all of this stuff in Excel, but if you think about a lot of the inputs into the methodology, such as call it PVT, or in some cases where you need the calculated bottom hole pressures, how important is it for, you know, efficiently utilizing a method like this to have, call it bottom hole pressure engines or hydraulic engines, PVT engines, and these methodologies kind of linked up in one interface?
Oh, I think it's indispensable. I mean, for a prototype, you know, I used Excel, but I had to get all the PVT data from somebody, Whitson or PVT Sim. I had to get the bottom hole pressure data from somewhere else, Harmony. So you can use Excel, but it is so painful. I do not recommend it to anybody. If I don't know if with, you know, now the technology belongs to Whitson, it belongs to Coterra. It's not mine anymore. I don't know if they'd be willing to share those Excel sheets with you for you guys to try it out on your own. I have absolutely no problem with them. You can argue with Matthias about that if you want to. But no, I do not recommend that. We, shortly after we developed the method, we created an internal web program similar to what Whitson is offering now for our engineers to use. Anything else is ridiculous.
Yeah, I would say we spend an inordinate amount of time trying to remove bias in individual interpretations, and the only way you can do that is by systematic calculations of flow and bottom hole pressure and modified Blackwell PVT tables that we derive from an equation state model through Whitson Plus.
Perfect. So just before we round off, Curtis, do you have any final comments to this before we stop the recording and wish everybody a good rest of the Wednesday?
Well, I just want to thank these guys and Cimerex for in a sense, releasing this to the public, so to speak. I guess y'all can hear me okay.
Loud and clear.
Yeah, and I think that I wouldn't worry about on the publication side. It's like the one had mentioned. It's really the technology. As long as the paper in some form reaches the public in some format, people will know who's developed it and or the foundation for it, and it will become used. I mean, there's just a long list of these papers out there that were never published that should have been published immediately and weren't. So I wouldn't worry too much about that. And, you know, as our good friend Keith Coates said, you know, why speculate when you can calculate? And so if you're a skeptic out there and it's great to be skeptical, just use the methods, do your calculations, and convince yourself. I think it's the best way. So I want to thank you guys very much for the presentation and for the technology.
Thanks.
Thank you. And on that note, we'll just close the webinar for today. We'll distribute the recording here later today, and wish everybody a good rest of the day and the rest of the week when that time comes around. Thank you.